Google is out with a new countdown that will excite the enthusiasts.
Prepare to question everything you thought you knew about.
The screen flickers to life, a deep black void pierced by a single shimmering point of light. It pulses, faint at first, then brighter, as if whispering secrets from the edge of the universe. A low, haunting hum builds, vibrating through your bones. Words fade in, slow and deliberate, each one heavy with promise. What if the stars are hiding something impossible? The image zooms out, revealing the infinite sprawl of space. Galaxies swirling, light bending, a cosmic dance frozen in time. Then a voice, urgent and raw, cuts through. Google's quantum team just found something in the James Webb Telescope's data. Something that could change everything. The screen flashes to a distorted infrared image of a galaxy cluster. Its arcs of light twisting in ways they shouldn't. The hum spikes and the screen cuts to black. This is only the beginning. You're standing at the edge of a discovery that feels like it could unravel reality itself. Google's quantum computing lab, a place where the impossible is wrestled into code, has just dropped a bombshell. The James Webb Space Telescope, humanity's greatest eye on the cosmos, might have caught a glimpse of something beyond our wildest dreams, a hidden dimension, a crack in the fabric of the universe. Not a theory, not a guess, but a signal buried in the light of distant stars. Picture this, a team of scientists hunched over glowing monitors in a sterile lab, their faces lit by the eerie glow of quantum processors humming at near absolute zero. They weren't looking for this. They were just testing their latest quantum algorithms, sifting through mountains of telescope data like prospectors panning for gold. And then, in the infrared glow of a galaxy cluster called Able 2744, Pandora's cluster, they saw it. A pattern that shouldn't exist. Tiny ripples in the light, like fingerprints of something otherworldly, something that defies the rules of physics as we know them. Let's step back for a moment into the heart of this cosmic mystery. Imagine you're floating 1,000,000 miles from Earth, where the James Webb Telescope drifts in the silent cold of space. Its golden mirror, a marvel of human engineering, gleams like a shield against the void. It's built to capture light that's been traveling for 13 billion years, light from the dawn of the universe itself. When it turned its gaze to Pandora's cluster, a chaotic smash-up of galaxies 4 billion light-years away, it saw something extraordinary. This cluster, a gravitational beast, bends light from distant galaxies into smooth, predictable arcs, a phenomenon called gravitational lensing, straight out of Einstein's playbook. But what the telescope caught wasn't just the expected curves. There were kinks, tiny distortions, like wrinkles in the fabric of space. At first, the scientists thought it was a glitch, a hiccup in the data. They checked the telescope's instruments, recalibrated every sensor, scoured every pixel for errors. But the patterns held. They weren't random. They followed a rhythm, a mathematical dance that whispered of something more, something beyond the 3 dimensions we call home. Now picture yourself in that lab, the air thick with tension. The quantum team, led by Google's brightest minds, wasn't hunting for extra dimensions. They were pushing their quantum computers to the limit, testing algorithms that could spot patterns no classical computer could dream of seeing. Quantum computers aren't like the machines on your desk. They don't crunch numbers one by one. They dance with qubits, particles that exist in multiple states at once, weaving through data like a mind reading the universe's thoughts. When they fed the Webb's infrared images into their latest processor, something clicked. The algorithms lit up, highlighting faint, repeating distortions in the light from Pandora's cluster. These weren't the smooth arcs of gravitational lensing. They were jagged, rhythmic, almost alive. The team stared at the screens, hearts pounding, as the data painted a picture that felt like science fiction. Could this be it? The first real evidence of a dimension we can't see, touch, or even imagine? You're probably wondering what these patterns look like. Close your eyes and picture a starry night, but instead of twinkling points, you see light bending into graceful arcs, like a cosmic kaleidoscope. Now zoom in. There, in the heart of the brightest arcs, are tiny ripples, almost invisible, pulsing in a sequence that feels deliberate, When the team mapped these distortions in 3D, they saw something that sent chills down their spines. The patterns formed a structure, a geometry that shouldn't exist in our universe. It was as if the light was brushing against something, a shadow cast by a higher dimension. The math backed it up. These distortions followed a fractal pattern with a dimension of 4.2, a number that screams impossible in a world with only 3 spatial dimensions. And here's the kicker. The patterns were consistent across multiple wavelengths of light, from near-infrared to mid-infrared. If this was just a cosmic trick, say a cloud of gas or a glitch in the telescope, it would look different in different wavelengths. But it didn't. It was the same everywhere, every time. Let's pull you deeper into this moment. Imagine you're one of the researchers, your coffee gone cold, your eyes burning from staring at the data for days. You're running the quantum algorithms again, tweaking every parameter, praying you didn't miss something. The room is quiet except for the hum of the quantum processor, a machine so cold it could freeze your breath. You're not just looking at numbers, you're chasing a ghost, a signal that could rewrite everything we know about the universe. The team leader, a woman with tired eyes and a fire in her voice, calls everyone over. She points to the screen where the anomalies glow in false color red against the blue arcs of normal lensing. This, she says, her voice barely above a whisper, this is what we've been waiting for. But waiting for what? A breakthrough that could confirm string theory? The idea that our universe is built on tiny vibrating strings living in 10 or 11 dimensions? Or a mistake that could waste years of work? The stakes are astronomical and the clock is ticking. Now step into the chaos of Pandora's cluster itself. This isn't just any galaxy cluster. It's a cosmic car crash, 4 massive clusters slamming together over billions of years, creating a gravitational maelstrom. It's a place where dark matter, that invisible force holding galaxies together, reigns supreme. The Webb's images show galaxies stretched into arcs, their light warped by the cluster's immense gravity. But those tiny ripples, those anomalies, they're strongest where the dark matter is densest. It's as if the dark matter is amplifying something, whispering clues about dimensions we can't see. String theorists have long said that extra dimensions might be curled up, impossibly small, hidden at scales a million billion times tinier than an atom. But in a place like Pandora's cluster, where gravity is pushed to its limits, those dimensions might leave a mark, and Google's quantum team thinks they found it. The world is watching now. Other scientists, from universities to observatories, are racing to verify these findings. They're diving into the Webb's archives, pointing other telescopes, like Hubble and ALMA, at the same patch of sky, running their own quantum and classical algorithms. The debate is fierce. Some say it's a fluke, a trick of the telescope or a bug in the code. Others, the dreamers, wonder if we're on the cusp of a revolution. Imagine it, a world where we prove extra dimensions exist. Gravity, matter, even time itself would need new rules. Textbooks would be rewritten, new technologies could emerge, and our place in the cosmos would feel both smaller and infinitely grander. But the truth is still out there, buried in the data, waiting to be confirmed or debunked. And just when the team thought they had a handle on it, they found something else in the Webb's images, something that made their hearts stop. The screen fades in from black, a slow zoom on a single glowing red ripple in the infrared image of Pandora's cluster. It pulses, almost like a heartbeat, against the serene blue arcs of gravitational lensing. The camera pulls back, revealing a chaotic swirl of galaxies, their light twisted by unimaginable forces. A voice, low and urgent, breaks the silence. They thought they'd seen it all. But then, this. The image zooms closer, the red ripple growing sharper, its edges jagged, unnatural. The music swells, a tense violin screech cutting through the hum. Something in the data is fighting to be seen, something that could rewrite the laws of the universe. The screen flashes to a scientist's face, eyes wide with disbelief, staring at a monitor. And it's not just in the stars, it's in the math. The image freezes on the ripple, now mapped in 3D, a ghostly wave rippling through space. The voice drops to a whisper. What happens when the impossible becomes real? You're back in the lab, the air heavy with the weight of discovery. The Google quantum team is no longer just chasing a signal. They're wrestling with something far bigger. That red ripple, that anomaly in the Webb's data, isn't just a glitch or a curiosity anymore. It's a clue, a breadcrumb leading to a truth that feels too massive to grasp. Picture the scene. A dimly lit room, monitors casting a cold glow on exhausted faces. The team leader paces, her voice sharp as she barks orders to rerun the quantum algorithms. The hum of the quantum processor is louder now, almost angry, as it churns through billions of data points. They've been at this for weeks, maybe months, sleeping in shifts, living on energy drinks and sheer adrenaline. Every time they think they've pinned down the anomaly, it reveals something new, another layer, another wrinkle in the fabric of reality. The patterns they found in Pandora's cluster aren't just holding steady, they're growing clearer, more insistent, like a message from the cosmos itself. Let's dive into Pandora's cluster again, because this place, this cosmic crucible, is the key. Imagine a battlefield in space, where four galaxy clusters have collided over eons, their gravity twisting space-time into knots. It's a place of raw power, where dark matter, that invisible glue of the universe, holds sway. The James Webb Telescope, floating 1 million miles from Earth, captured this chaos in stunning detail. Its golden mirror, chilled to -370 degrees Fahrenheit, sees through cosmic dust to reveal galaxies so distant their light began its journey when the universe was a toddler. But it's not just the beauty of these images that's gripping the team. It's what's hiding in them. Those tiny ripples in the light, those micro distortions, are strongest where the cluster's gravity is most extreme. It's as if the universe is screaming, "Look here! Something's different!" And the math agrees. The anomalies follow a fractal pattern, a dimension of 4.2, impossible in our three-dimensional world, but eerily close to what string theorists have predicted for decades. Now let's pull you into the heart of string theory. But don't worry, it's not a lecture. It's a story of a universe far stranger than we ever imagined. Picture reality not as solid, but as a symphony of tiny vibrating strings, each one a billionth of a centimeter long. These strings don't just exist in the three dimensions we know: length, width, height. They need more room to dance, 10 or 11 dimensions, curled up so tight we can't see them. It's like the universe is a book, and we're stuck reading one page, blind to the others folded inside. String theorists have spent decades dreaming of these hidden dimensions, but they've never had proof. Until now, maybe. The patterns in Pandora's cluster match models where gravity leaks into these extra dimensions, bending light in ways our physics can't explain. Imagine you're holding a flashlight in a dark room, but the beam twists and curls as if slipping through cracks into another world. That's what the Webb's data is showing, a light that's touched something beyond. Back in the lab, the tension is palpable. The team isn't alone anymore. Scientists from across the globe are joining the hunt, their own telescopes trained on Pandora's cluster. Observatories like ALMA in Chile and Hubble in orbit are rescanning the same patch of sky, looking for those telltale ripples. University labs are adapting Google's quantum code, tweaking it, testing it, trying to break it. The air is thick with skepticism and hope, a clash of cautious minds and wild dreamers. Some say it's microlensing, tiny stars or gas clouds bending light in unexpected ways. Others point to software quirks, data compression errors, even cosmic rays hitting the Webb sensors. But every test, every rerun, keeps pointing to the same conclusion. The anomalies persist. They're real, consistent, and maddeningly precise. The team leader pulls up a new visualization, a 3D map of the distortions. It's breathtaking, a web of rippling waves like the shadow of a higher dimensional object cast into our reality. The room falls silent again, not out of awe, but fear. What if this is real? Let's zoom out to the stakes of this moment. If these anomalies are what the team thinks they are, we're not just talking about a new discovery. We're talking about a seismic shift in how we see the universe. Imagine waking up tomorrow knowing that space isn't just three-dimensional, that there are layers we can't see, dimensions where gravity might flow differently, where time itself could bend. It would be like discovering the Earth isn't flat, but a sphere, or more, a hypercube we can't yet fathom. Textbooks would be shredded, new fields of science would explode into existence, and technologies we can't even dream of might follow. Quantum computing, already a game changer, could leap forward, tapping into principles we don't yet understand. But there's a flip side. If this is wrong, if it's a cosmic mirage, years of work could collapse into embarrassment. The team knows this. They feel the weight of history breathing down their necks. Now let's take you to the edge of the cluster, where the dark matter connection comes into play. Dark matter, mysterious, invisible, holding galaxies together like an unseen hand, might be the key to this puzzle. For decades, we've known it's there, bending light, speeding up galaxy rotations, but we've never seen it directly. Some physicists think dark matter isn't a particle at all, but a shadow of extra dimensions. Picture gravity leaking into these hidden realms, weakening in our world, mimicking the effects we call dark matter. In Pandora's cluster, the anomalies line up perfectly with the densest pockets of dark matter, as if they're two sides of the same coin. The team maps these overlaps, and the patterns are uncanny, too precise to be chance. It's like finding a footprint in the sand where no one should be walking. The question isn't just, what is dark matter anymore? It's, what if dark matter is a doorway? The global scientific community is now a pressure cooker. Online forums buzz with heated debates, skeptics tearing into every line of code, believers pushing for bolder experiments. At CERN, physicists are planning to smash particles at higher energies, looking for energy that might vanish into hidden dimensions. In basement labs, delicate instruments test gravity at scales so small they defy imagination, searching for the tiniest deviations. Space missions like ESA's Euclid and NASA's Roman telescope are gearing up to map the cosmos with unprecedented detail, hunting for more signs of these extra-dimensional whispers. The Webb itself is scheduled for new observations, its instruments fine-tuned to zero in on those anomalous regions. Every night the team waits for fresh data, their hearts racing, knowing each image could bring them closer to truth or disaster. But then something shifts. Late one night, a junior researcher, bleary-eyed and half asleep, notices something in the latest batch of Webb images. It's not just the ripples anymore. There's a new pattern, fainter, almost invisible, buried in the noise. When they enhance it, the team freezes. It's not just a distortion, it's a signal, repeating in a way that feels almost intentional. The room erupts in chaos, voices shouting over each other, as the screen glows with a new image, one that makes their blood run cold. The screen pulses with a faint, rhythmic glow, a new pattern flickering in the infrared depths of Pandora's cluster. It's not just a ripple anymore, it's a signal, repeating, deliberate, like a code etched into the fabric of space. The camera zooms in, the pattern sharpening into thin, thread-like structures weaving through the gravitational arcs. A low, eerie drone fills the air, building to a crescendo. The voiceover, now trembling with intensity, cuts through. This isn't just light bending. This is something calling us. The screen flashes to the lab, where scientists stand frozen, their faces bathed in the glow of a monitor displaying the signal. One researcher whispers, "It's like the universe is talking." The image shifts to a 3D visualization, the threads twisting into a shape that feels alive, almost sentient. The music spikes, then drops to silence. But what is it saying? And who's listening? You're in the lab now, the air electric with panic and wonder. The Google quantum team is unraveling, their voices overlapping in a frenzy of questions and theories. The new pattern, the signal, changes everything. It's not just a distortion in the light from Pandora's cluster. It's a sequence, repeating with a precision that feels unnatural, almost purposeful. Picture the scene. Monitors flicker with data, the quantum processor hums like a living thing, and the team leader stands at the center, her hands shaking as she pulls up the enhanced image. The signal is faint, buried in the noise of the Webb's infrared data, but once they isolate it, it's unmistakable. Thin, thread-like lines weave through the gravitational arcs, forming a pattern that pulses in a mathematical rhythm. It's not random. It's not a glitch. It's something more, something that makes the team question not just physics, but reality itself. Let's step into the heart of this moment. Imagine you're one of the researchers, your heart pounding as you stare at the screen. You've spent months chasing anomalies, convincing yourself they're signs of a hidden dimension. But this feels different. The signal repeats every zero point 0.3 arc seconds, a cycle so precise it defies any known astrophysical process. When the team maps it in 3D, it forms a structure that twists and folds, like a shadow of something higher dimensional, something alive.